Hello, everyone. As Alexei said, my name is Valentin. I am right now head of LLM Research and Development Department in MWS AI. I think there is a few. Next slide will be about me. The first slide is agenda. The agenda is like that. Important point right now that this lecture will not give you like cutting-edge research results. That was not my intention. That was not my goal as the organizers asked me to do so. So my goal is here to give you some basic understanding of how the LLMs developed from the, let's say, from scratch, from the first ideas to the current state, and maybe a few current directions of development, but only a few. If you will have questions regarding some specific technologies or something, we could discuss them after the lecture as it is a current format. So this is the slide about me. So as I said, I'm head of language model research and development department. Have few dozen papers about LLMs and have vast experience. If you want, you could check on the slide. So as I said, we want to discuss today the LLMs, let's say, from scratch. So the first will be foundations. Next, we will discuss transformers shortly, of course. Then more recent things like GPT and agents. And at the end of it all, it will be current directions aside of LLMs, which are closely related. So the first part, the foundations. This could be a little bit boring, but this is what it is based on. I mean, all of the current natural language processing, the work with texts and even words. I mean, the speech and that stuff. It is based on this understanding. So we need to start from the simplest thing. What is the language model? Before I explain it, please raise your hand who think that you know what the language model is. Not all of you, that's good, because many people has not quite right definition in their head about the language model. The language model itself is really simplistic, overly simplistic thing. This thing is it is coming from the simplest definition of a language. How we can say that something, some words I'm saying right now, is a part of some language, English currently. So we can say this if these words are accepted by a speaker in this language. So what does it mean accepted? This is actually a tricky concept, and we will not dig into this, but we instead will have the definition of it by the probability function. We will say that there is a vocabulary, and this vocabulary has a finite number of words. For the actual languages, this is not true, but just for now. Finite number of words, and we'll say that phrase in a sentence is just the set of words. That's it. That's enough for us. And our probability function will give some probability to the any set of words in the vocabulary. That's it. So this is a language model. Another way to look at the same problem is that we can give a probability for the next word given the previous words in a set. This is the same. This is the same definition, but it's how it's based inside. Okay, hopefully this is more clear now. So our main idea, the main goal of all the stuff happening in the recent years and starting maybe 50 years back is just somehow estimate this probability, and that's it. Okay, so to understand how we do this, we need to work with chain rule. You, of course, know the chain rule. So the main idea is that you can estimate the next word probability given the previous one, and given two previous one, three previous ones, and so on. So the idea here is that we'll have the conditional probability of the current word given all the previous ones, and this will be the probability of next word, and if we multiply all of them, we will get the probability of the whole phrase. So we'll get the language model probability. So this is also called autoregressive. Autoregressive because we are basing our next prediction on the previous ones. Okay, so the actual sampling, the basic concept of sampling is that we, given this probability, we can sample from this probability the next word, and we'll get this word as a part of a context. So it's pretty easy. Next thing, how we actually get the language model. So all before that, that was like general description which could be applied to any language model at all. But this is more about training. So we can train a model which could maximize the likelihood of the current given number set of words. So if we get the set of words, we can give it a probability, and we if we get this probability it's actually have, this is actually important point because nobody knows the actual probability, but we can estimate it basing on some definitions, basing on some ideas, and I think this will be the next slide, but before that, the maximum probability, maximum likelihood. If we reformulate it using the logarithm, because we cannot work in a computer with really small numbers, logarithm will give us numbers we can work with. We can say that this maximum likelihood is the actual perplexity. So the perplexity, in a way of saying, is how your model is surprised by the current data. So this is from the very beginning, and this is how we still measure the probability. So still measures the quality of our language models. Okay, regarding the language models themselves. So as I said, all that was before, it was applied to any language model as we have it. But if we want something specific, we could start with simplistic n-grams. N-grams still useful. The last paper on n-grams I've read, I think, a year or two ago. It was from DeepSeek. So you could think that this is old technology, but it's still useful. And the idea here is that we have count of n-gram, and we divide it by count n minus 1 gram. So the shorter n-gram, and we get the conditional probability as we think. So it is not the actual probability, but we estimate it using these rough counts from our corpus. The important point here, why I'm actually using this n-gram, why I can use it. This is based on the specific mathematics. It was Russian Soviet mathematic Markov, who who actually worked on the stochastic processes, and he said that we can assume that the past is actually, how to say that, the future depends on the past to some extent. It's not depending on all the past to the beginning of the world. It depends only on a few steps back. And this assumption we call Markov assumption, and we basing all our developments on this assumption. So we say that for us, the probability is dependent only on n words, and that's it. All the n plus 1 plus 2 plus infinity words are actually not really interesting to us, since they are not defining our future, our current and future. So in practice, the n-grams we work with, mostly 4 grams, 5 grams at most, and this is how it works. So it's really short sets, but still they could be pretty useful. Okay, so the problem with this useful technology is the sparsity. I think you understand, but let me explain maybe shortly. So if we have the set of words from a corpus, our corpus is finite. It is always finite. We cannot work with infinite corpuses. And in finite corpus, not all word sets are present. That means that if we need to estimate the probability for the new set, new to the corpus, so it's not presented in a corpus, and if we want to estimate the probability of it, the probability will be 0. This is by definition. And this is an issue, and this issue is called sparsity. And there are some, of course, some workarounds for that. We can do some smoothing, we can do some additional things. It's not really that important. We always could improve a bit, but it's not like solving the issue fundamentally. So as I said, we cannot make more of the n-grams. There are some specific problems, like it cannot work with bigger context than we work with, like 4 grams. But this can be important. We cannot even store all the wanted n-grams if they are more than, say, 5 grams. You can compute how many n-grams you should store if you have 5 grams and 1 million words in English, for example. And there are some additional issues. I will be not like describing them thoroughly. The idea that n-grams good, but we need some new technology, and we actually switch to the next technology. And this next technology is, of course, neural nets. I think all of you just waited when I skip all this old stuff and come to the interesting stuff. And the interesting stuff is neural nets, and the neural nets are actually pretty old also. The people started to think of neural nets, I think, 70 years ago or something. And the idea here is that we can predict the next word using the classic softmax. So softmax is a soft maximum function, which is gives us an option to have the smooth function, which could be used as a probability for the next word. So it is still the word, the language model. It is still predicts the next word, but now it uses weights of a neural network to store the information instead of counts. Okay, so It is good, but it is not good enough. The next step is that we cannot work with the variable length context, and we want it since, as we know, there are a lot of data which could be dependent on the really long context, and this is totally okay. I think it's more, for example, for say lawsuits or maybe some enterprise documents, a lot of things which requires reasoning on long documents, and the previous technologies cannot do this. So the guys invented RNNs. The RNNs is a pretty simplistic idea. So we store some memory. We store this memory and use it for the next step. On the next step, we process the memory, we process the input, we combine them here, and this is actually enough to get the our context and maybe infinitely long context. Actually, in practice, of course, it's never infinitely long, and it has really short context, but it could be much bigger than 5 grams. It could be up to say few hundred words. It's still really short for current by current customs, but we can do the improvement here also. The next improvement will be, I will describe it later, but before that I need to describe to you the backpropagation through time. And the backpropagation through time is how we actually learn, how we teach our language model. So we have some loss function. It is still cross-entropy, still perplexity, but we now apply it to the hidden states, and we apply it to the infinitely long set of hidden states. Now you should say to me that, well, stop. You're saying that it is infinitely long, and this is cannot be true. And you're right, it cannot be true. And actually, in practice, we never use the infinitely long sequences. We use finite sequences, and this is called truncated backpropagation for time. Propagation through time, and this is actually again Markov assumption. So it's again hit us. We cannot get rid of Markov assumption. The backpropagation through time has some issues like vanishing and exploding gradients. In short, it means that more step you do back through time, it's your gradient either explodes, so you will get the bad updates, or becomes 0, and then you have no update. Both are bad, and both need to be dealt with, and they actually do. Some of the way, it's not like the only way to do this, but it's kind of good way. It's RNNs, more the next step of RNNs, it's LSTM. Maybe you heard of, just curious, who heard of LSTMs? Before this lecture, I mean, yeah, few people. That's nice. Thank you. So LSTMs, it's a much more complicated thing. It has concept of gates. The gate concept, it is when you're say have some gate. If you want or do not want to use the specific information, so you just gating the vector, and maybe you get rid of it, or maybe you use it. We'll be not we will be not delving inside the LSTMs. It's really interesting, but it's not our case right now. The next thing is sequence-to-sequence idea. Sequence-to-sequence, when we get 2 RNNs, LSTMs maybe, and the first RNN we consider as encoder, and the second as decoder. Now you hear the words you should be familiar with. So you have these encoder and decoder, and encoder reads what you want it to read, and decoder decodes, so it generates the text you want it to output. And between encoder and decoder, there is a bottleneck. There is a really small needle hole which need to be passed through, and this is actually really lossy compression here, and that was the main issue with RNNs back in the day. Not our day, of course, but back in the day it was really important. So we get through the first part. I think it's the most boring one, but I'll try to surprise you. The breakthrough. It's called breakthrough because some guys, actually it was a Russian guy from Belarus, Belarusian maybe, and he invented such thing as attention. It was 12 years ago, and this attention was actually intended to solve this bottleneck problem. So between the encoder and decoder, we have only one vector to pass, and we want to get rid of this needle hole. And if we want to get rid of it, we want somehow to understand what information we need. So instead of passing one vector, we weighting all the vectors from encoder, and we weight them basing on their closeness to the vector we want. This is actually decoder state. And if they are close to decoder state, then we get more information from them. So this is softmax summation of the vectors from the encoder, and we pass this to decoder. And that allowed us to solve the issue with context. Of course, it's not solving it at all. Yes, because why we need all this stuff with transformers and that. But now we at least understand how it was going. So the idea is that we have we can have other view for this. Instead of saying that we summing up, we can say that we have a lookup. So if we have retrieve the information from the database, if you want, in big quotes, but still the base with vectors, and if the information is relevant, somehow this function G is a relevancy function. If it's relevant, then we get this and we get it to the output. So this is the other way to look at the attention. And the next step is the attention from transformer. So the attention from transformer, it's a bit more complicated thing. So the basic attention is easy to understand. The attention transformer, it also uses the same metaphor for retrieval. So we have the query, we have key and values. So we store the values, we use keys to access the values, and we use query to get the right keys. So we compare queries with keys and get the values. And the actual the actual formula is that Q multiplied by K, transponent of course, and we get the softmax of it, so we get the actual attention, and we get the values. And this is how we get the information. So we retrieve the information we need to get this. The attention is a really interesting thing. It's a kind of soft alignment. Now the word alignment is used for the different thing, but I was starting when the alignment meant that we align words between themselves, for example, in machine translation or in some other task. And that means that we have some word and we see that its translation is like that. This is really important. Of course, here it's not the translation. Here is the attention between the words inside one sentence, but the idea is the same. We want to understand on which we need to actually get our attention on. Okay, so what I'm trying to say is that it's before that step, all I was saying that was so-called cross-attention, the attention between encoder and decoder. And now we're working with self-attention when we are working inside the text itself. So we are not working with the two different texts, one on the input, one on the output, but instead we're working with with one text, and we're trying to understand how a text is how to be said, how it's dependent on each other inside. So we want internal structure of a text, and we get it using this attention. Of course, it's maybe huge words here, but it's a kind of way to look through on it. Okay, so as I said, the attention could understand as differential retrieval. So we retrieve some information from something. Before that, we have the retrieval from the encoder to decoder, and now we have retrieval of related text parts. So the other text parts inside the same text, we retrieve them and we're trying to use it. Okay. So why the attention is actually better than just using AirNets? Because the attention allows us to skip this bottleneck. It is workaround for this bottleneck, and we pass more information from encoder or from our model to itself, and this is better, and it's better because we have the path which is shorter, it's context length, and it's important we can parallelize it. This is a really important thing, because the recurrent neural nets, based on what they are recurrent, we cannot parallelize them at least easily. Of course, there are some tricks, but these tricks, it's not the core of the technology. And this is why the overwhelming winning of the transformer in the recent years, because it was released about 2017, and in a few years it becomes the standard, leaving all the other architectures really aside. It's really far from the center of the public attention. And because the transformer is really, really useful. The transformer itself, it's kind of easy thing to understand. Actually, initially, the transformer was encoder-decoder architecture as before. So we have encoder transformer and decoder transformer, but we'll skip this part and we'll get to the only decoder attention, decoder transformer. So we have some the pre-processing. We have multi-head self-attention. Self-attention you already know. Multi-head we'll discuss a bit later. Some normalization, feed-forward, again normalization, and we have the output, which is softmax in our case. So it's easier and it is parallelable and it is much more effective. This is why we get this the transformers everywhere. The multi-head, as I said, this is a really important concept in transformers, because if you have experience working with the computer vision, with convolutional neural nets, you know about the so-called kernels or filters, which is inside these convolutions. And these heads, this is actually kind of filters. So they work the same way. They work in parallel, and they do slightly different work, which we can adopt to use for some different NLP tasks. So it could be syntax, coreference, a lot of stuff. I will be not actually describing them here. If you have some more questions, you could always ask. But what is important that we have several attention mechanisms applied at the same time. This is the main idea you should get from here. Okay, before that, I have shown you a picture of the transformer, and maybe you have noticed that there was something that is called positional encoding. Positional encoding, this is actually kind of important thing, because the transformer, it have no notion of position. I mean, the attention cannot understand which word is first, second, or I don't know, the last, the thousandth, any word. It's for attention, they are all the same. But maybe you remember that before that we discussed the recurrent neural networks, and in recurrent neural networks we have natural ordering. So the first word is first, the second is always after the first. So this is important, and we actually want to keep this information, because the word order is important. In some languages like Russian, it's maybe not so important, but in many languages like Chinese or English, it's crucially important. And we need to keep this information, and to keep it, we use specific function to define the positional encoding. The positional encoding is a way to define a vector for a position. Nowadays, nobody uses this funny sinus and cosinus encoding, which is coming actually from the radio engineering. I'm actually, my bachelor's was mostly in radio engineering before, so it's for me it's like really nostalgic thing. But now nobody uses this. Mostly uses specific vector. How to be said? Turning vector function. So we turn a vector for position for model to understand how far these words are, and that's it. Next thing is about FFN, fully connected network, or feed-forward network, which is the same. It is used for the attention, for the transformer after attention, because in attention we only mixing the data. Maybe you could get this idea from the formula, but if you're not, the idea is that when we get this attention function, when we have weight for input vector, we just mixing them. We're not translating them to something other. But with this feed-forward network, FFN, we get some new information. So mostly in transformer, we informally consider FFN as storage for the memory, while the attention is a way to process the data. So this is like informal way to look at the things, but it's kind of working, of course, to some extent. Okay, so other important thing is residual connections in transformer. I was skipping that on that picture, but here it's important to say that the issue with vanishing exploding gradients in RNNs were kept in mind while the guys from Google invented transformer. So they say that we will get the residual connection, which is also comes from the convolutional neural nets. And if we get the residual connection, like a side of FFN and a side of attention, we'll get the whole vector in the whole gradient, and this gradient will not vanish in any way. So this is good, but this is why we need some normalization. If we passing through all the information, we need to normalize it so we keep the information we actually processed. I was saying that there were some encoder and decoder things, and transformers actually started to use as encoder decoder. Next few years we were all working with encoder transformers only. It was BERT and that stuff. I think you should heard of BERT, but I'm not be concentrating on BERT here. After that, we all switched to decoder transformers. This is GPT-like models. And the most importantly, this is all important, but the most importantly, we understand, I mean in the community, we understand that the decoder transformer is just works better. That's it. It's like end of sentence, the period. So since it's working better as an encoder, we have no need in other stuff. We just use it and we'll be using it more. Okay, so only one thing that should be said here, since we're using the decoder, which is, as I said, working better, but it has its own issues. The main issue for the decoder in transformer is that when we actually decode, that means that there is some data we work with which is not present yet, which is kind of in the future. And that means when we have this data, we do not, it's important, we do not want our transformer to access this data. So we introduce masking, which allows us to mask the data the transformer shouldn't use. Because, for example, in training, it should train, or in the inference, there are no dates. There are only garbage in this position. So we need to mask, and we will be shortening the mask step by step and coming to the end with no mask. So we're starting with the whole mask and shorten mask word by word, processing the data on and on again, and getting to the final result. And it is still better than the encoder, which is more efficient, but has not that good quality. Okay, so the issue with that, as I said, since we're processing it again and again, is the issue is that the self-attention has n squared complexity. The complexity of n squared. That means that for the data to process, we need a lot of things done. It is actually worse. This is important. This is worse in the complexity sense than RNNs. So the RNNs, the outdated technologies, it seems, it is more efficient than transformers. But we use transformers because they are better. And everybody in the industry is actually understanding that the situation is not okay. But we still use it, and we trying to somehow address this. There are a lot of ways to address it. I will be not concentrating on them here, unfortunately. Maybe my colleagues will. Okay, so regarding the transformers, why we actually use them? Because they are parallel. They are not efficient, but parallel. And this is why we use them on the GPUs. There is no this hidden stack bottleneck as before. If we train bigger transformer, we mostly, not always, but mostly getting better results. So this is why the current models are about trillion parameters. And with RNNs, that was not working, unfortunately, because RNNs were really, really complicated technology, I would say. Okay. From the like from the perspective, the tokenization, I think I skipped this, the positional coding with embedding of a word, multi-head attention, and the prediction. So this is how the transformers work step by step. Okay, so this is the decoder transformer as a nutshell. So the next thing will be for the GPT itself and other important stuff in it. So the important stuff in it is that we have decoder not only transformer, GPT-like, as I said, and the important point will be for the tokenization. I think it will be a slide for that, and it is efficient. It is still minimizing the simple perplexity, simple cross entropy, with just pre-training it given the next token prediction. And now this is a new word, pre-training. So we pre-train a model on a simplistic language modeling task. So I started from the defining of language modeling, and for language modeling, we have the cross entropy, and it is still with us. I think it will be still with us in a few years at least. But after that, we can use this as a base model for the next improvements. Okay, so interestingly, that GPT-2, the model which were trained only on the data like language modeling. So it only predicts the next word, but on a few billion words. And after that, the authors, I think it was OpenAI, yes, it was OpenAI. They actually found out that this model can do more than just next word prediction. It could answer questions, but it was never taught to answer the questions. It really shifted the paradigm. Now it seems to be normal, but back in the day, we have models which were trained to do one task. And here we have a model which can do different tasks, even not being trained on them. This is really a leap forward. The GPT-3 in 2020, it's a really big model. It's like 100 times bigger than GPT-2. And its emergent abilities are amazing at the time. It can do the machine translation, could do summarization, do everything. Of course, nowadays it seems to be really outdated and really stupid, but back in the day it was really a really interesting model. It is still a big model, and as we now understand, it's really undertrained. So 175 billions, it's really big model even now, and now I think models with 9 billion parameters are much better than this huge monster. But instead of that, we can understand this using so-called scaling laws. I will be not describing you in detail the scaling laws, but the idea is that we can, given such a formula, this formula I think comes from Chinchilla, if I'm not mistaken, yes, from Chinchilla, and it described to us how many data we need to actually get the model of some quality, basing on our definition of what the quality is. So we can understand that if we give more training time, logarithmically more data, we get better results. So we all basing on these Chinchilla laws. Of course, we're trying to improve the quality beyond Chinchilla, but it is still there. It is basing for us. Next thing is about this GPT-3 abilities. So the GPT-3 ability, for example, one is so-called in-context learning. I don't like this. This is a break as far as I remember, so it's okay. I have almost a half of my material now, so. Okay, so as I said, the GPT-3 is really interesting model because it has more abilities. For example, the ability of so-called in-context learning. As I said, I don't like the in-context learning as a word, as a like phrase, because it is not learning by itself. It's not any single weight is changed during in-context learning. We just provide a model with example inside its context, and that's it. So I mean, that's it. That's enough for a model to be able to solve a new task for it. And this is really useful, and I think you are using it every day. Maybe like maybe not all of you, but if you ever tried GPT, DeepSeek, I don't know, any other model, I mean large language model which are available now, then you could get the idea of what I'm trying to say. So you just provide, say, DeepSeek with a question and give it some context, and it answers you with some quality, maybe good. So this is really important stuff. Also, if you give a few examples, like K, it's called few shot, and few shot is also important. It's in most cases it's have more quality, but still good, and even in zero shot. So even without any context, model may be able to solve your task. Maybe not, but you could try, and I think nowadays it could solve many tasks. Not always, not all of them, but still many of them. Okay, so I was saying that there is tokenization we use. So the tokenization, I'll spend maybe a minute here. Tokenization is actually really important task in NLP, I mean in text processing, because it's not that easy to tokenize words, tokenize the text by words. It actually may be not intuitive for the people with languages like Russian, where we have this white space, and white space divides the words between themselves. But still, if you tokenize, you not always tokenize a word by itself. So you maybe want to tokenize two words together, or maybe you want to tokenize a word inside, so you could split a word to the parts. For the languages like Chinese, where there is no white space between words, the tokenization is kind of obvious. So this is the main task for text processing. Like back in the day, you try to tokenize the words like in the proper way to get the actual meaning of a sentence. The transformers introduced, actually it was invented before transformers. The BP itself, it is actually a bit reformulated zip algorithm. Zip is archiver. Maybe you've heard of about zip, and the zip was invented back in the 70s. BPE is actually doing really simplistic thing. It is just getting the most frequent pair of tokens, the letters, maybe words, it's not important, and keeping it as a new word in a vocabulary. So you grow your vocabulary and getting shorter representation of your text. And since you're getting this shorter representation, then you get the easier processing. And more importantly, it's not only easier processing, it's easier to generate. So generating by BP now is a standard. Actually, not exactly BP, it's some other method, but it's pretty easy nevertheless. So I was saying that we use the BP not only to pre-process the text and process the tokens. We use it also to generate. And for generation, we need some, how to say it, if we want to generate, even using by BPE, why we actually need to use BPE for generation? We need to use BPE for generation because when you're trying to generate, you have softmax. As you remember, we started from the softmax generation, and we still use softmax for generation. But if you have a huge vocabulary, for example, in English, as I said, about 1 million words, maybe 2 million already, and it is really huge vocabulary, and it is never will be good enough for prediction. Instead, BPE is typically about, say, 30, right now maybe 100, 200,000 of tokens, and this is enough not only for English, but for many, many languages. And this is why we use the BPE. But actually, when we want to produce from even the shorter distribution, shorter vocabulary by softmax sum distribution, we need some adjustment to softmax to be more efficient. For example, the temperature gives us the shape. It takes different shape for the distribution. Of course, it's in the same family, but it's in different shape, so the sampling will be different with some different temperature. The top K is how many biggest scores we keep, and top P is about the smallest set. So this is the idea of these parameters is to get the sampling as efficient as possible. Of course, it is maybe not the not solving the sampling by itself, but it makes it much more efficient. Okay, so a few words about the GPTs, because it's important. In the first GPT was in 2018. It was not really that good at this year, but in the next version it was good enough. GPT-3 showed everyone that is really good. GPT-4, starting from GPT 3.5, the all models are closed, but fortunately the guys from OpenAI, they have released some of their developments, and many other people also, of course, contributed to this, and we will come into this in the next slides. Okay, so what we have here is that the GPT by itself, as I said, is trained or pre-trained, as we used to say now, only to just predict next word. We started from it being language model. It is still language model, but we understand that the predicting next word, in many cases, it's important. In many cases, it is not enough, if we want to predict the next word, it's not always means that this is helpful to a user. So the user cannot maybe get all the information or answer she or he wants. So this is why we need to somehow make our distribution more how to be said, closer to the actual distribution in the actual neural network. I mean, the biological neural network inside, for example, my brain or your brain. So we need somehow the distribution be closer to the human one. And we need to do something about it. So we make so-called post-training. So yes, so there is pre-training and there is post-training we're now working with. And this post-training, it has different parts. We'll be discussing them right now. But we need to understand that we will get the our model as so-called policy for the like we're trying to get our model to be responsible to make some decisions in, say, a dialogue. So it's different paradigm on looking on the language model. So before it was just predicting next word, and now it decides what to answer the whole entire sentence. It's a different paradigm, and we need some different tools for that. What we do here? We do here the SFT, so-called supervised fine-tuning. The supervised fine-tuning, it is actually pretty the same as pre-training, but the important part for the supervised fine-tuning, it is made on a small amount of really good data. So it's clean, it's useful, it's good data. On this good data, we train our model in a way that it is trying to predict good answer. So with maximizing the probability of the whole answer here, it is still actually the same cross entropy. It's just written in a fancy way, but it's still cross entropy. And it allows us, for example, to teach our model some format and style. Maybe it's not. It seems to be not that important, but for the people, for their how they actually look at the text, it's important. And that was like invention, how we can improve the how to say improve the impression of the text from a person, not only the quality of an answer. This is why we need so-called instructions. And these instructions, this is the data set written by a person, by some people, which provide some examples how we actually can answer. For example, write me an email for my colleagues about the, I don't know, Smile Summer School. So if I'm saying that I'm writing an email for the colleagues, that means that I need some formal style in specific format. For example, I need to have this first opening, like dear colleagues or something like this, in specific way, and the word should be written in a specific way, and should be closed like sincerely yours, something like this. And this is why we actually need here the instructions and instructions how to write such a mail and such not such a mail. A lot of stuff need to be done with this, and the SFT is not enough here, so we need some additional thing to work with. Like I said, this is the some sample how to write for models. For example, this is the system prompt. Yeah, so like use helpful assistant. I think it's the most common prompt in the universe. And here we have the question from the user, and we need to generate an answer. And we cannot use this system prompt in SFT, because in SFT, yes, we can use it, but it will be not that efficient. And we will better use it for some other, in some other way. For its other way, we need to understand how we actually work with these instructions. So if the instructions exist, does our model follow the instruction? And we need to understand that, and there are some evaluations on that. For example, if eval and other evals, which are allowing us to understand if it follows. And actually, evaluation is an important part, but I'll skip it entirely. About the limits. The targets for the SFT still noisy. So if we use system prompt with, for example, even with some samples, with all of this stuff, we'll not get the good results right away. For example, if we have answers for 2 plus 2, it does not mean that it can answer us 3 plus 3 or 3 plus 1000. It's not easy to understand which data we need and how we can provide good examples for good instructions. We need somehow to work with better way to represent our needs. And this is so-called LLM. We go beyond the SFT. What does it mean? That means that we will, instead of teaching our models step by step, sorry, not step by step, teaching our models word by word, we'll be teach it to answer the entire question and judge by entire answer. And this is another perspective. As SFT, as I said before, it is just more fancy cross entropy, and we need more additional things here. The LLM, so-called, it was invented by OpenAI. This is really huge in our field, and what we have here that there is SFT. After that, we have to train reward model, and after that, we do the reinforcement learning with this reward model, which gives us rewards instead of a person. So we train a model to give us an answer like a person, which actually evaluating an answer. And after that, if we get the evaluation an answer from a person cannot evaluate all the answers we need. So we train a model and we use it to train our first model, which is SFT1. Here we have so-called Bradley-Terry model. Bradley-Terry model is actually it's pretty simple. So we have input as X, we have two possible answers, and we want to say which answer is better, the first one or the second one. And Bradley-Terry just saying to us that the reward between like first answer and the second answer should be maximized if we want the sum of answers be better. And this is how the actual reinforcement learning is working. As I said, unfortunately, I have no time to delve here, but what is how it's working in a nutshell is that we have a model, and this model is compared to some reference model, and we want our model to be better than our reference model. So the reward is maximized. That it means that it produces better answers, but it is still should be close enough to the reference model, so it will be not breaking the evaluation. Okay, so what is the KL divergence? KL divergence, this is a way to say how two distributions are different. I think you understand what it is, but what we need, how we use it here. So we have reference model, we compare it to our model, and we're saying that if our model is far from our from the reference model, that means the KL divergence will be big, and we do not want this. This is because it could be broken, it could be not answering at all, just trying to please the reward model. This is actually happening all the time. So the issue with RLHF, it is unstable. As I said, we have the reward model, which is trying to reproduce human judgment, but this is not that easy way to do. We have the reward hacking, as I said before, reward hacking, that our model tries to hack the reward model. And the reward model is only trying to be a good model to model what we want, but it's not representing the whole universe. And it's could be broken. And also, it's really costly to train. So maybe we can do here better, and it is we can do this actually. And if we have a look at the Bradley-Terry model, we can understand. Of course, I'm not invented here. That was guys from Stanford which have invented here, and I think this is the most important thing in natural language processing for the last decade. And this is inside here is that. So if we compare the models here, the same model we train and the reference one, and we will have some additional z function which we can actually ignore. And if we ignore this, we get the formula that we can compare the first answer with the second answer by, this is pretty much Kyle divergence, two Kyle divergence we compare between each other, but actually that means that here we can use directly our policy models, our language models, and they just produce the answer, and we just using the simple cross entropy to predict the quality of the whole answer. So as I said, this is key thing in the NLP for the last decade. And they found out that we can use simple cross entropy function to judge not by word but the whole sentence. And since it is like this, then we need we have no need in this reward function, in the labeling, all the stuff. We just have two answers and judging which is better, and that's it. So as I said, DPO is much better. It's actually not RL. It is RL, but training not as RL. So it's much easier to train. It's much simpler. We have no need in reward function, and we can do this offline. We have no need in online, and that was a huge event. So we have really good models after that, and a lot of stuff has been done with this. But of course, we never stop, and the next step is GRPO. GRPO, it is online. It is like DPO, but it's more online thing. So it's we have several answers generated, and we just optimizing the policy on several answers, based on which answer is better inside a group, not inside the like in a pair, but in a group. And what is here? We have the reward, and we just want our model to give the rewards for each in a group. And we get the advantage if we get some model, some answer which is much better than the other. So we improve the quality of the model based on the one answer in the group which is different from the others. So we trying to judge by the group of answers instead of two, and this actually happening online, and this is why it's better. Unfortunately, yes, GRPO requires more resources for us, I mean for training, but it gives better results than DPO in many cases now. I think it will be more and more for the next steps. So GRPO in practice has been introduced in DeepSeek R1 a year ago, and In DeepSeek, there is a new thing that arises. This is reasoning. I think you heard of reasoning. The reasoning thing is a new step when we have our model to think on the answer before the actual answering. This allows us to get better results, and this is really good. I think I will not be concentrating here. Let's go beyond. So the next thing is agents. It's not that obvious for some reason, but the agents, this is actually the dialogue systems. Maybe you heard of dialogue systems. They have been developed for last 50 years. And the agents is just dialogue systems. And what we actually have, this is just fancy way to say that we have a model which is working in some specific environment when it can do some actions. The action could be some tool, so we can use tool to call, I don't know, database. We can call some external service, whatever. This is an action, and we do this action with a model. So we train our model using DPO or DRPO to actually call a tool and get some results. Next thing is that is about RL. I was skipping the RL itself, but I already said one word, action, so our model can do the action, but it also has some, as it's called in RL, observation. So our model reading not only the input from the user, it also reads the output of a tool and use it to produce its own answer. Actually, it's additionally we can do several steps in the actions, maybe reasoning, maybe additional stuff. So we have so-called closed loop. So we process not inside the neural network. We process having the words generated by a model. We generate these words, and these words allows us to get better model, better answer from a model. So to do this, we need so-called chain of thought planning. So we have chain of thought. This was actually invented before. It was invented for the language models. Language models can can do chain of thoughts basing on the on examples, but here we can use them to produce some reasoning steps. Also, we have graph of thoughts and plan and execute approaches. It's not really important. The important part is that we have thoughts, and these thoughts can include some tool calling. It includes some plans. So we plan how we can do step by step the complex task. Another thing which is really important is a long context. You remember that we started from the 4 words in a context. Now we are working with documents with million words in a context. And these million words, we need to somehow to process them. And transformers can process this, but it requires a lot of memory. We want to maybe work with some additional thing like RAG, retrieval augmented generation, when we process not the whole million of tokens, but the small piece of, say, 1,000 of tokens to answer a question. And we can use some external memory. We can formulate maybe in some exact words, maybe in some vectors, and store some information externally of a model and use it from time to time to get better results. Okay, so this is reasoning, and it could be multi-step, and it could critique it by itself and could correct itself. So this is a way we want it to be, and we could teach it to critique itself and to do this stuff. So this is also important right now. This is what is the models are aiming today. Uh, and another thing which is, I think, crucial and is what is the all agent stuff has started from is this is code execution. So our model could produce a code and function call actually is a code, and we could execute function call or code has been generated and get the answer. For example, we can generate by a model instead of understanding that we need to sum, for example, 1,000 and I don't know 650. We produce Python code, for example, to actually do the summing, and if we do the summing, then we get the exact answer, because the model cannot do the exact computation inside. It's only fuzzy computation, but using the external tools, it's easier. So we can produce the code, and it really helps a lot. So the next step, and I think it's right now the top of the current developments, this is so-called agentic loop. So we now have tools, we have memory to store, we have planning, and all this stuff is combined to get the agentic loop. So we get the goal, we have model to understand if this goal is achievable, how we can achieve it, get the plan, and go step by step for this plan. So we make not the next word, we make the steps in this thought process. So this is next level. So there are a lot of stuff which is happening around this, but I will be not stay delving here. So actually agents are great, but they have of course a lot of stuff which is not good yet. So there are some errors which has been done, the misinterpretation, the bad calls, the reliability which can rely on agents. So a lot of things that cannot be done by agents right now, at least reliably. And there are a lot of room for improvement here, and a lot of people are working on that. So you could also join here. And for example, safety is open question in many agent skills. Okay, so but in many cases, like code writing, the agents are really good. Some analysis, workflow automation, it's really good, and I'm using it myself, and I think that you could also try, and maybe it will be helpful for you also. But let's go beyond the agents. What's actually going on in the industry, in our area? Not only agents, but what else? As I said, the transformers are great, but they have their downsides. The downsides I have already said, for example, complexity, memory, and so on. What have been invented to overcome this? Instead of this, we can do, for example, diffusion models. Diffusion models is actually inside the transformer. Inside it is a transformer, but it's different way to do the decoding. So I think this image is better. So idea here is not we are predicting word by word, but we instead predict several words simultaneously. So we predict, for example, 500 words in 64 steps. So we could say 10 times faster generation. Of course, maybe it's not that good. It has its own downside, but it's still useful. And I think we have some lectures on the diffusion models on this school. So hopefully you will get more information about this. The diffusion for text is not easy because, as I said, text has natural ordering, and diffusion is actually ignores the ordering, at least not ignores, but for diffusion the ordering is not the same as we used to. So it can produce a word in the beginning, then in the middle, then again in the beginning, and so on. So I will be not having a lot of words about this here, but you can ask a question. Another thing which is important is RNNs. So RNNs, as I said, this is an old technology, but this old technology is still can come back. So it is more efficient, as I said before, but it has issues. It is not that effective. So instead of using the old technology, we'll use new technology, RWKV. I think it's, I don't remember who is this exactly. Is this some Chinese team? They invented this thing. So they invented new way of attention. This is actually attention. So this attention is just using the previous information step by step. So it is actually recurrent, but it's much more efficient than before. So the advantages, as I said, it is constant memory, as any RNN. It is linear in time because it is RNN. And the downside, it is have some issue with memory as RNN. So it is still RNN, but it's better. So you could try it for your models. As far as I remember, the Tianwen, the last maybe a few versions, it also includes Mamba, which is actually not RNN. It's a state model, but it still shares the same ideas. So yeah, state space models. This is kinda RNNs doing the other way. So they cannot be represented as RNNs or as fully connected networks basing on these coefficients, which could be defined in the in the inference time. So we can train it is as RNN, and we could infer it as a fully connected network. So the state space models are kind of RNNs, but transformer style in a way. So they are a bit more complicated thing. As I said, I will be not concentrating here. And the last but not least thing, I think this is the most hot topic for the past half a year. This is hierarchical reasoning models. This is, in a nutshell, really easy stuff. We have a small model and we have a large model. Small model is doing all the work. It's producing new words constantly, but sometimes it could call for a huge model to make huge thoughts and understand some difficult task and explain it to a small model, and small model will produce the actual answer. So I will again not be stopping here. If you want, you could get the slides and maybe some literature I have been provided here. We started from the counts. We get from recurrent to attention to the scaling and to preferences, and we not stopped, but we are currently at action. But of course, all the stuff before, it is still presented, and it is still can be researched if you want to. Now we have more and more developments in RLHF, different things. We have more and more developments in agents memory and that stuff, other types of models. And there are a lot of things that could be done in the field, and hopefully you will get the information from school and from other colleagues, maybe from me, and you get hands-on experience with at least some of aspects of it. There are open problems, as I said, the reliability, efficiency, alignment. I'll skip alignment entirely in this presentation. Let's keep it this way. Evaluation and generalization, which is still not the way we want. So if we not trained a model for some task, it may be not that good at this task, but we want to change this. Okay, so this is you can do the you can look at the some papers which have been provided here. And the best way just run code with some coding agent, and you'll see the results, how much understanding you get. And before I actually end, I invite you to participate in the challenge. We have opened the challenge. You can join. This is Agentic Coding Challenge, which is on the ICSE International Conference on Software Engineering, which is A-star. And if you will be winning this challenge, you could get your report published at A-star conference. So if you're interested, please join. The submissions are not opened yet, but please join the page, and you'll get the information soon. And now that's it. I'll be able to answer your question. Thank you. Any questions? Too much of information, I see. Yeah. I understand this is a bit overwhelming. Yeah, there is a question, please.
Okay. The question is that during my personal usage of large language models, I feel that sometimes I do not even contribute with the ideas to the vibe coding process, okay. But the only thing I do is manage some flow between one model, another model, and I just connect them. And I feel that the reason I'm useful in this context is that while people that are professionals in their domain, they are constantly learning from their birth to their death with one specialized domain. While the large language models only can reuse the previous context, but they do not adapt to current project and the current user, only by memory, for example, between different chats. And my question that it seems to me that that's the next big thing, that the models would well, maybe rise with people, or maybe they would use their current subjective experience and internalize it, somehow learn. So the question is that am I the only thing that is thinking about this, and does this thing have a name? And what are the perspectives of that? Thank you.
Yeah, so thank you for your question. This is actually, there are some guys in the industry who shares your thoughts. For example, Anthropic just recently released a J space, I think, something like this. This is Jacobian space they have found out in their model. I personally really skeptical about this subjective experience of a model and that stuff. I think that we cannot define subjective experience. We cannot actually measure how it is, what is the subjective experience, how we can train it. I think that training in a production, it's an interesting topic and will be done. But if we are talking about the subjective experience, I think it's more about philosophy, not about the our LLM experience.
Thank you. Well, what about my personal use case and the use cases of many people that have their own domain? Actually, I need to describe the context of the project, maybe my patterns of thinking that are typical for the domain. So if the model would learn while production, would it allow different models to adapt to different people, different domains, and how would that be organized? Would there be specialized weights for different models, or how would it be that?
Yeah, thanks. I got your question. So I don't know. So some guys were trying this. I think OpenAI still has this option to train I think it's small LoRa. They are not saying this is LoRa, but we understand this is LoRa. Small piece of information for your usage of the model. And I think it is kind of useful, but nowadays it's easier to just store the memory, such skills. You could like write your own skills, at least ask a model to write skills and reuse it when you're using it again. So it's kind of, right now the memory is on the user side, is external memory to a model. So we're not changing model, we're changing memory. Maybe there will be changing in this field, but right now it's like this.
Some hierarchical LoRa for different people, for different domains too?
I actually don't know. This is, we don't know. Can we do this? Kinda can, because for example, together with my colleagues, we have written a paper in a bit different domain. It's for machine translation, but we used the single LoRa for the entire group of languages, and after that reused it to train LoRa for specific language. This improves the quality. Yes, it is kind of working, but is it the best